All right. Uh, it's very cold today. Um, okay. Preemption disabling. Okay. So because the kernel is preemptive, a process in the kernel can stop running at any instant to enable a process of higher priority to run. So just to review, preemption. Preemption is when a process in the kernel is is going to go into a ready state or wait state due to the kernel kicking it off for whatever reason, due to like some sort of scheduling policy, and also switch it with another process to run. Okay? So this means a task can begin running in the same critical region as a task that was preempted. Okay? So if if in this case, um, we don't hold a if a task doesn't hold a lock, right? Um, what ends up happening is that when that task is in this critical region, or like I guess what we say like a region of code where um, shared data shouldn't be modified by multiple tasks. Um, what ends up happening is that one task could be in a specific critical region and then get preempted, and it turns out another task was in the same area, and that's why you get that race condition. So to prevent this, the kernel preemption code uses spin locks as markers of non-preemptive regions. If a spin lock is held, the kernel is not preemptive. Okay? Because then what ends up happening is that things start to just busy wait. Because the concurrency issues with kernel preemption and SMP are the same, the kernel is already SMP safe. This simple change makes the kernel preemptive safe too. Or so we hope. But in reality, some situations do not require a spin lock, but do need kernel preemption disabled. The most frequent of these situations is per processor data. So that is if, let's say you have tasks that execute on each processor individually, you may not need preempt. You may not need, I guess, locks to prevent that preemption problem, because basically the data that you're trying to modify is only unique to that specific CPU core. So if the data is unique to each processor, there might be no need to protect it with a lock, because only that one processor can access the data. If no spin locks are held, the kernel is preemptive, and it would be possible for a newly scheduled task to access the same variable as shown here. So task A tries to manipulate the per processor variable foo, which is not protected by a lock. So we don't have a lock here. But then task A gets preempted, and then task B is scheduled. Task B tries to manipulate the per processor variable foo, so that shared variable in the CPU, and then task B completes. Task A is rescheduled, and then task A continues manipulating that shared variable foo. So, consequently, even if this was a uniprocessor computer, the variable could be accessed pseudo-concurrently by multiple processes. So remember, pseudo-concurrency means that you simulate that concurrency by preempting processes one after another. And if you have like tasks or processes that are operating on the same region in code, by that preemption, they may seem like they're operating simultaneously. So normally this variable would require a spin lock to prevent true concurrency on multiprocessing machines. If this were a per processor variable, however, it might not require a lock. So to solve this, kernel preemption can be disabled via preempt disable. This call is to solve this kernel preemption. Alright, to solve this, kernel preemption can be disabled via preempt disable. This call is nestable, so you can call it any number of times. For each call, a corresponding call to preempt enable is required. The final corresponding call to preempt enable re-enables preemption. For example, so we disable preemption in the kernel by doing preempt disable, and then we do whatever we need to do, and then we re-enable kernel preemption. So easy API. But the problem, I think, is going to come where how do we know when to use that, right? So the preemption count stores the number of held locks and preempt disabled calls. If the number is 0, the kernel is preemptive. If the value is 1 or greater, the kernel is not preemptive. Okay, so preemption count stores the number of held locks and preempt disabled calls. So this number is always going to be changed based off of these types of calls. Okay, so this count is incredibly useful. It is a great way to do atomicity and sleep debugging. The function preempt count returns this value. See table 10.11 for a listing of kernel preemption related functions. Okay. I still don't understand when we would actually know how to do this, but let's keep going. As a cleaner solution to per processor data issues, you can obtain a processor number, which presumably is used to index into the per processor data via get CPU. This function disables kernel preemption prior to returning the current processor number. Int CPU. Disable kernel preemption and set CPU to the current processor. So get CPU here is probably implicitly doing the same thing as this one here, preempt disable. And then from here, we can manipulate per processor data, and then we just re-enable kernel preemption by doing put CPU. So what's the difference? Oh, okay. So if you wanted to disable preemption, kernel preemption, in like the context of wanting to modify per processor data, this is actually the better helper to do it, apparently. So, okay. Ordering and barriers. When dealing with synchronization between multiple processors or with hardware devices, it is sometimes a requirement that memory reads, loads, and memory writes, stores, issue in the order specified in your program code. When talking with hardware, you often need to ensure that a given read occurs before another read or write. Okay, so this is actually a real thing. Because your compiler, when you're compiling code, it tries to go through some sort of optimization where it could potentially rearrange code in a way that it deems more optimal. And sometimes that could also be a bad thing because it could rearrange things where it turns things that may have seemed like it was okay out of order to actually being legitimately, like logically out of order, which could result in a different result. So additionally, on symmetrical multiprocessing systems, it might be important for writes to appear in the order that your code issues them, usually to ensure subsequent reads see the data in the same order. Complicating these issues is the fact that both the compiler and the processor can reorder reads and writes for performance reasons. Yep, this is the one I'm talking about. Thankfully, all processors that do reorder reads or writes provide machine instructions to enforce ordering requirements. Okay, so we can force the compiler to not do that for certain blocks or chunks of code. Guessing there's yet another function call that we have to call in order to prevent that from happening. So I guess when the compiler sees something like that or the CPU sees something like that, it won't attempt to reorder. I guess I should also say that it's not just the compiler that does this, it's probably the CPU too, because the CPU does take instructions in chunks and then reorders them so that it executes them for faster, I guess better performance this way. So that's also like another scenario. So it makes sense why like to stop that reordering from happening, it has to be through like code. So it's like it gives like the compiler or like the CPU that specific hint. It is also possible to instruct the compiler not to reorder instructions around a given point. These instructions are called barriers. I should just start reading it more before stopping and speaking. Essentially, on some processors, the following code may allow the processor to store the new value in B before it stores the new value in A. Essentially, on some processors, the following code may allow the processor to store the new value in B before it stores the new value in A. Okay, so like this is a situation where the compiler or the CPU gets this chunk of instructions and sees it as this. Okay, well look, A equals to 1, B equals to 2. Well, they both don't seem to rely on each other at all, so it doesn't really matter. I can say B equals to 2, A equals to 1, and it'll still be the same thing. So both the compiler and the processor see no relation between A and B. The compiler will perform this reordering at compile time, and the reordering will be static, meaning that it'll actually end up being like burned into the program text. And the resulting object code would simply set B before A. So literally it'll be reordered to B equals 2 and then A equals 1. The processor, however, could perform the reordering dynamically during execution by fetching and dispatching seemingly unrelated instructions in whatever order it feels best. So then, okay, even though the compiler rearranged things, it's still up to the CPU to determine like whether or not it will even like not reorder or reorder it again based off of the situation of how it's like processing things at the moment. So the vast majority of the time, such reordering is optimal. So it's really good most of the time. There is no apparent relation between A and B. Sometimes the programmer knows best though. So sometimes this can be wrong. So let's see in a situation where it can be wrong. Although the previous example might be reordered, the processor would never reorder writes such as the following because there is clearly a data dependency between A and B. So if A equals to 1 and then we do B equals to A, this cannot be reordered because if we do B equals to A and then A equals to 1, B would have the old value of A if it was initialized to another value prior before being assigned to 1. So reordering this would be really bad. So I'm pretty sure that the compiler or the CPU won't do something like this if it sees it, because reordering would not work in this case. So neither the compiler nor the processor, however, knows about the code in other contexts. Occasionally, it is important that writes are seen by other code and the outside world in the specific order you intend. So like in case if we really truly need to make sure this never ever gets reordered, even though it seems like it wouldn't be reordered, there is a way. So this is often the case with hardware devices, but is also common in multi-processing machines. Okay, let's see. So the RMB method provides a read memory barrier. It ensures that no loads are reordered across the RMB call. That is, no loads prior to the call will be reordered to after the call, and no loads after the call will be reordered to before the call. Okay, so it's like a wall. So should I draw? I'll draw. Okay, so it's like a wall. So let's say you had I guess line 1, line 2, and then you had this RMB call, and then line 3. Okay, so then what does it say? It says no loads prior to the call will be reordered to after the call, and no loads after the call will be reordered to before the call. Okay, so basically if we had loads here, like any loads here, loads, and then loads here. Loads meaning I think assigning, right? No, not assigning. Reading. Any of these any lines here that reads data, okay, won't be reordered. I guess in a way where it would kind of jump past the RMB call right here. So this is my understanding. So it's like if let's say line 2 had to execute before line 3, like in a way where we cannot do line 3 before line 2, you would actually have this RMB call in between the two. Okay, so that's the barrier that I think they're talking about here. And this is for loads. So RMB is for loads. So anytime we're reading something, I think, yeah. Or is it reading or writing? Let's see. Stores. Yeah, okay. So we have a writing version too. So the WMB method provides a write barrier. It functions in the same manner as RMB, but with respect to stores instead of loads. It ensures no stores are reordered across the barrier. So same approach. Now the MB call, which I'm starting to get this feeling that this might be more common. The MB call provides both a read barrier and a write barrier. No loads or stores will be reordered across a call to MB. So I am guessing, oops, I just reordered this. Yeah, I am guessing that we commonly use, this is one of the more common scenarios. So they have line 1, you have line 2, and then you'll just have like a MB here, and then line 3. I'm guessing this is used more often. You want both in this case. It is provided because a single instruction, often the same instruction used by RMB, can provide both the load and store barrier. A variant of RMB, read barrier depends, provides a read barrier but only for loads on which subsequent loads depend. That means all reads prior to the barrier, okay, are guaranteed to complete before any reads after the barrier that depend on the reads prior to the barrier. Got it? No, I don't. All reads prior to the barrier, so this barrier, this RBD, let's call it read barrier depends. Okay, fine, let's say the full name. Okay, so all reads prior to the read barrier depends are guaranteed to complete before any reads after the barrier that depend on the reads prior to the barrier. So any reads that come before this read barrier depends must complete before any reads after the barrier, okay, after the barrier that references things made, like references memory locations, I guess, that happened before the barrier. Sure. Okay, so basically, so basically it enforces a read barrier similar to RMB, but only for certain reads, those that depend on each other. Yeah, okay, so that is the gist. Okay, so only the reads that are after the barrier are affected by the barrier if they're referencing things or that come before the barrier. Okay, that's kind of smart. I don't know how it does it. Okay, so anyway, on some architectures, read barrier depends is much quicker than RMB because it is not needed and thus a no-op. Okay, let's consider an example using memory barrier MB and read memory barrier RMB. The initial value of A is 1 and the initial value of B is 2. Okay, so initial value A is 1. So you know what? This is going to confuse me. So let's do this. Huh? Oh. How do I slingshot? Come on. Okay. I need to clean up my desk. Okay. It's getting cramped. Alright. Okay, so here it is. So what is the initial value of A is 1 and the initial value of B is 2. So in this case, A equals 1, B equals 2. Okay, cool. Because this is confusing without knowing the initial values. Okay, so without... Okay, so now, if we say A equals to 3 on thread 1, with this memory barrier, okay, A would basically result in being 3. That's easy. Okay, and then here, since A equals 3 completes, B equals 4. Sure. So final result 3 and 4 from thread 1, but C equals to B. But then since this is a memory barrier here, this has to finish first before thread 2. Okay, I think that's the point. So C would also be 4. Now read memory barrier happens. So D would be, in this case, 3. So I'm claiming then the value of C is going to be 4. And then D is going to be 3 in that case. So I think that's going to be what they're trying to say. Let's see. So without using the memory barriers on some processors, it is possible for C to receive the new value of B, whereas D receives the old value of A. Okay. So for example, C could equal 4, what you expect, yet D could equal 1, not what you expect. Using the MB ensured that A and B were written in the intended order, whereas R and B ensured C and D were read in the intended order. Oh, so that is correct. This sort of reordering occurs because modern processors dispatch and commit instructions out of order to optimize the use of their pipelines. What can end up happening in the previous example is that the instructions associated with the loads of B and A occur out of order, and the RMB and WMB functions correspond to instructions that tell the processor to commit any pending load or store instructions, respectively, before continuing. So let's look at a similar example, but one that uses read barrier depends instead of RMB. In this example, A is 1, B is 2, and then the P is... Okay, so this is a pointer, and pointer P is the pointer B. Okay? So we know A is 1, B is 2. So A becomes 3, and since... Okay, so this is a memory barrier. This has to finish, and then P is going to be the address of A. Okay, so this is a different number. This will be a different number. Okay, so since this is a barrier, PP will be basically this updated version here, and then this is referencing the same thing here. But this is a write, right? Is that... No, that's a load. That's a load. Your load... What is this? This is a load or a store? Huh. But anyway, so the read barrier depends only protects you from loads that depend on the previous. So this would be safe. Yeah. Because you do need to load P, right? In assembly, you need to load the PP. You do need to load the PP to dereference that value. So B should still be 3 in this case. Let's see. Again, without memory barriers, it would be possible for B to be set to PP before PP was set to P. Okay, yes. Okay, cool. The read barrier depends, however, provides a sufficient barrier because the load of PP, yay! We got that one. Depends on the load of P. It would also be sufficient to use R and B here, but because the reads are data dependent, we can use the potentially faster read barrier depends. Note that in either case, the MB is required to enforce the intended load store ordering in the left thread. So the macros SMP RMB, SMP WMB, SMP MB, and SMP read barrier depends provide a useful optimization. So on SMP kernels, they are defined as the usual memory barriers, whereas on uniprocessor kernels, they are defined only as a compiler barrier. You can use these SMP variants when the ordering constraints are specific to SMP systems. The barrier method prevents the compiler from optimizing loads or stores across the call. Oh, wait, legit? Oh, okay. So all this had been in context to this processor, the CPU, to prevent that reordering. But this one, barrier, is specific to only for the compiler. Okay, so for these were all CPU at runtime. And then this one is static for the compiler. Okay, sure. The compiler knows not to rearrange stores and loads in ways that would change the effect of the C code and existing data dependencies. It does not have knowledge, however, of events that can occur outside the current context. For example, the compiler cannot know about interrupts that might read the same data you are writing. For this reason, you might want to ensure a store is issued before a load, for example. The previous memory barriers also functions as compiler barriers, but a compiler barrier is lighter in weight than a memory barrier. Hold on. All right. Indeed, a compiler barrier is practically free because it simply prevents the compiler from possibly rearranging things. Table 10.12 has a full listing of the memory and compiler barriers methods provided by all architectures in the Linux kernel. Okay, so yeah. Interesting. Okay. So note that the actual effects of the barriers vary for each architecture. So good to know. For example, if a machine does not perform out of order stores, so you don't have that type of behavior in your CPU. X86 don't do out of order stores, so writing things. WMB does nothing. You can use the appropriate memory barrier for the worst case, that is the weakest ordering processor, and your code will compile optimally for your architecture. Wait, you can use the appropriate memory barrier for the worst case, that is the weakest ordering processor. Does that mean the one that has the least memory barrier features, or the like, for example, if we were to think about the writes and stuff like that, then we wouldn't need a WMB, because if we're programming against like x86 inclusively, then we wouldn't need that. Okay, I don't know what worst or the weakest means here, but I'll assume that we should. Oh no, I think, yeah, okay, so yeah, it makes sense, because if you do a WMB with that assumption that it's going to work, like when you're going to code and you insert a WMB, you're assuming that you're making a lot of assumptions, when it could be that if this code runs on x86, that does nothing, and then your assumptions would break in this case. At least my assumptions. So yes, you would have to program for the, I guess, the crappiest, less feature processor in this case. Okay, so that means you would have to put, like in this case, I guess this would be a case where we need to put a lock. Yeah. Okay, so conclusion. This chapter applied the concepts and theories of the last chapter to help you understand the actual methods provided by the Linux kernel for enforcing synchronization and concurrency. We started with the simplest method of ensuring synchronization, atomic operations. We then looked at spin locks, the most common lock in the kernel. Good to know, spin locks are the most common lock, and I think they're the easiest ones too. Which provide a lightweight single holder that busy waits while contended. So remember, spin locks will cause busy waits on contenders. So basically people or tasks that want to grab a hold of the spin lock while it is already being held by another task. So next we discuss semaphores, which is a sleeping lock, meaning that if A lock is contenders will just go to sleep. And it's more general and use cousin, the mutex. So a mutex is just basically a semaphore where you can only have at most one lock holder because semaphores allow multiple lock holders based off of the count that you initialize. So mutexes are just basically a special case of semaphore where you only have one lock holder maximum. Following mutexes, we studied less common, more specialized locking primitives such as completion variables. So this would be useful for like event handler and events. So if you had a specific event you're waiting for, you would use completion variables. Say let's take like a timer or something. You wanted, well, not like. Yeah, let's say you were waiting for like a bunch of things to complete within a certain period of time. Those things would signal that complete call, while the thing waiting for it would use that wait for completion API. And then seek locks. We poked fun at the BKL, so the big kernel lock, which is like obsolete now, so don't use it. Looked at preemption disabling and tackled barriers. It has been a wild ride. Yes, this was a tricky, difficult chapter. So armed with this chapter's arsenal of synchronization methods, you can now write kernel code that prevents race conditions, ensures a correct synchronization, and correctly runs on machines with multiple processors. I personally don't think I'm there yet, but I think if I were to just keep practicing and coding, it'll come more natural. Okay, let's dive quickly in. Well, let's use some of the remaining time to just get ahead and start on our timers and time management chapter here. Okay, so, wow, this person was hardcore studying this chapter. It's been a while since I've seen highlights from this person. Okay, so timers and time management. So the passing of time is important to the kernel. A large number of kernel functions are time-driven as opposed to event-driven. So that doesn't mean that nothing is event-driven in the kernel. It's just that we do have a lot of cases in the kernel where operations are time-driven. Okay, so some of these functions are periodic, such as balancing the scheduler run queues or refreshing the screen. And that's true. Refreshing the screen, you have to be timer driven, because if you want to hit 60 frames per second or 60 hertz, you have to refresh the screen every 16 milliseconds or so. They occur on a fixed schedule, such as 100 times per second. That will probably be like the scheduler, switching or context switching or checking to see if a context switches are needed 100 times per second. The kernel schedules other functions such as delayed disk I/O, so when to finally flush the data from memory to disk at a relative time in the future. For example, the kernel might schedule work for 500 milliseconds from now. Finally, the kernel must also manage the system uptime and the current date and time. So that's like the most basic one. Like the kernel needs to know the date. So like take for example here my system clock. It's actually about 5 minutes off now. Since I rarely ever turn off this desktop, something probably got out of sync eventually. But I don't know, my physically my computer has been kind of weird. So just today I can't like things. Yeah, you probably can't see it in the capture, but anyway, note that okay, that happened again. Okay. Okay. Note the differences between relative and absolute time. Scheduling an event for 5 seconds in the future requires no concept of the absolute time, only the relative time. For example, 5 seconds from now. Conversely, managing the current time of day requires the kernel to understand not just the passing of time, but also some absolute measurement of it. Both of these concepts are crucial to the management of time. Moreover, the implementation differs between how events that occur periodically and events the kernel schedules for a fixed point in the future are handled. Okay, wait, so there's different ways, there's different implementations for time too. There's different time implementations on intervals, okay, so periodic things and then things that are scheduled for the future. Okay, so there's different ways to actually implement this time stuff. Events that occur periodically, say every 10 milliseconds, are driven by the system timer. The system, go away. The system timer is a programmable piece of hardware that issues an interrupt at a fixed frequency. So it is a piece of hardware that's separate that will just fire interrupts at the system in certain periods of time, certain intervals of time. The interrupt handler for this timer, called the timer interrupt, updates the system time and performs periodic work. So it's in charge of also keeping track of literally the system's time and whether or not there should be something done at that moment. So I'm guessing it also helps with keeping track of regular time in general. The system timer and its timer interrupt are central to Linux and a large focus of this chapter. The other focus of this chapter is dynamic timers, or the facility used to schedule events that run once after a specific time has elapsed. So basically, this is where you would like kind of schedule something for like to happen 3 seconds from now. For example, the floppy device driver uses a timer to shut off the floppy drive motor after a specified period of inactivity. The kernel can create and destroy timers dynamically. That's cool. So these, I'm guessing these timers are just like objects. The kernel can just like spawn timers and just free them as necessary. This chapter covers the kernel implementation of dynamic timers and the interface available for their use in your code. What is it? More accurate, time-driven events are also event-driven. The event being, okay, never mind. Okay, so the kernel notion of time. Certainly, the concept of time to a computer is a bit obscure. Indeed, the kernel must work with the system's hardware to comprehend and manage time. Okay? The hardware provides a system timer that the kernel uses to gauge the passing of time. So very important detail is that, system timer is a piece of hardware that issues the interrupt to basically your kernel to do something periodically. And that's driven through those interrupt handlers. So the system timer works off an electronic time source such as a digital clock or the frequency of the processor. The system timer goes off, often called hitting or popping, at a pre-programmed frequency called the tick rate. When the system timer goes off, it issues an interrupt that the kernel handles via a special interrupt handler. Okay? Because the kernel knows the pre-programmed tick rate, it knows the time between any two successive timer interrupts. This period is called a tick and is equal to 1 over tick rate seconds. Okay, let's read that again. The kernel knows the pre-programmed tick rate, sure. So therefore, it knows the time between any two successive timer interrupts. So let's say, if we know the tick rate, we know then how often periodically another tick is going to happen. Okay, so it could be like every 100 milliseconds then. So this period is called a tick. So the tick is 100 milliseconds, or it could be 10 milliseconds, or it could be 50 milliseconds. Okay, and is equal to 1 over tick rate seconds. This is how the kernel keeps track of both wall time and system uptime. So if I said tick rate was 50 times, then basically a tick is 1 over 50 seconds. What is 1 over 50? Wait, yeah, 1 over 50. So it'd be like 0.02 seconds, and then if we multiply that by 1,000 for milliseconds, is that how you? Yeah, every 20 milliseconds in this case. Is that true? Is that right? I guess. Okay. So a tick would be 20 milliseconds if the tick rate was 50. So this is how the kernel keeps track of both wall time and system time. Wall time, the actual time of day is important to user space applications. So that's the actual time, is the wall time. Okay, so is that like real life time then? The kernel keeps track of it simply because the kernel controls the timer interrupt. Okay. A family of system calls provides the date and time of day to user space. Okay, so we have specific system calls that will allow processes in user space to get the time and day. Okay. The system uptime, the relative time since the system booted, is useful to both kernel space and user space. So both user and kernel space can query for the system uptime. A lot of code must be aware of the passing of time. The difference between the two uptime readings now and then is a simple measure of this relativity. Okay. The timer interrupt is important to the management of the operating system. A large number of kernel functions live and die by the passing of time. Some of the work executed periodically by the timer interrupt includes updating the system uptime, updating the time of day, and in an SMP system, ensuring that the scheduler run queues are balanced, and if not, balancing them. Okay. Running any dynamic timers that have expired, and updating resource usage and processor time statistics. So all of this, like all of these things here, depend on the timer executing correctly, and knowing basically the passage of time. Okay, so it would make sense. All of them relate to time, right? Like updating the system uptime, updating basically this time here, and then scheduling, and then anything that was like scheduling is in process scheduling, and then scheduling work, right? The schedule, like running any scheduled work, and then just basically stats. Some of this work occurs on every timer interrupt. That is, the work is carried out with the frequency of the tick rate. Other functions execute periodically, but only every n timer interrupts. That is, these functions occur at some fraction of the tick rate. The section, the timer interrupt handler, looks at the timer interrupt handler. Okay, yeah. All right, so tick rate, hertz. The frequency of the system timer, the tick rate, is programmed on system boot based on a static preprocessor defined hertz, Hz. The value of so this is just basically, what is this? This is a macro or a macro variable, where you call it Hz. So you'll reference the frequency of the system timer in the kernel code as Hz. So if we were to go here and I guess actually let's do this. Hz. Yeah, so you see all these references to Hz. The Hz here, the Hz here would refer to that frequency. So the value of Hz differs for each supported architecture. So whether or not you're x86 or ARM, I guess. On some supported architectures, it even differs between machine types. Okay. The kernel defines a value in asm param.h. The tick rate has a frequency of Hz hertz and a period of Hz 1 over Hz seconds. Okay. For example, the default x86 architecture defines Hz to be 100. Therefore, the timer interrupt on i386, which is 32-bit x86, has a frequency of 100 Hz and occurs 100 times per second, every 100th of a second, which is every 10 milliseconds. Oh, so my math was correct on the 50 one. Other common values for Hz are 250 and 1000, corresponding to periods of 4 and 1 millisecond, respectively. Table 11.1 is a complete listing of the supported architectures and their defined tick rates. Okay, so we could easily find this in code, right? So let's just take a look at x86 in code. Let's see that. So if we were to go to here, where is it? asm.param.h. So we were to look for, what is it? param.h somewhere. Okay, so here's all the architecture here, asm param.h. So here, like x86, oh, asm generic param.h. Okay, so you'll have hz right here. Okay, interesting. Now we had param.h for, I don't know, IA64, the Itanium. So this will be config hc. So this one is more configurable. Or, oh, okay, here, 1024. But technically this is wrong. But some OLAPs still refer to it. The proper way to get the Hertz value is via the sysconfig scoctic. Okay, that's. I'm curious now, like how much of this is sprinkled throughout. Okay, so this is more correct. This is for ARM, is 100. Okay, so anyway, when writing kernel code, never assume that Hertz has any given value. This is not a common mistake these days because so many architectures have varying tick rates. In the past, however, Alpha was the only architecture with a tick rate not equal to 100 Hertz. 1024. And it was common to see code incorrectly hard-coded to the value of 100 when the Hertz value should have been used. Okay, so yeah, when you're programming, use this value. Don't hard-code frequency here. So the frequency of the timer interrupt is important. As you already saw, the timer interrupt performs a lot of work. Indeed, the kernel's entire notion of time derives from the periodicity of the system timer. Picking the right value, like a successful relationship, is all about the compromise. All right, I'm going to stop here for now. So we'll continue on the next video. Thank you.